have to be told? I'll tell you. This is the 43rd lecture, and we are going to discuss today the other two kinds of networks consisting of two kinds of elements only. So far we discussed only LC, inductance and capacitance, and the motivation was that most of the practical networks which are to be used in communication should preferably be lossless or LC. However, there do arise occasions on which you require to synthesize resistance capacitance and resistance inductance driving point functions, and this is what we shall discuss today. You recall the Foster 1 for LC. Foster 1 form for LC network is you can have an inductance, a capacitance, and then a number of inductors and capacitors in parallel. This is the most general form for LC. Or F2. F2 is also the most general form for LC. Okay. Now, we can take any one of them. We can take any one of these general forms, and by virtue of the knowledge that we have hopefully gained through a discussion of LC networks, we can derive the properties of RC and RL networks without going into much of derivation. All the facts that we have gathered for LC can now be transferred to RC in a very simple manner. For example, if we take an RC network, this is for LC. If we take an RC network, obviously the most general form for RC network can be obtained from this simply by removing all inductances and replacing them by resistances, and therefore my most general form for RC network shall be of this form. We shall have a resistance and a capacitance in general, then a number of resistor capacitor networks in parallel. Okay. This comes, let us say this is the ith one. This is the ith RC network in ith RC parallel RC network in series. Okay. Let us say this is our infinity. Why I use this symbol infinity shall be clear in a minute, and let us say this is C0, okay, and let us say this is Ri and this is Ci. This is the most general form for an RC driving point function. It is not that other forms are not possible, other forms are possible, but this is one of the forms, and as I said, we can start with any of the forms and go over and derive the properties. Now, to look at these properties, first let me explain why I use this subscript infinity. You notice that at s equal to infinity all capacitors will be short, and therefore this will be short. All resistors will be shorted by these capacitors, and therefore obviously if this is z of s, z of infinity is equal to R infinity, isn't that right? And this is why the symbol, the subscript R infinity. Why I used this C0 is also obvious, that at s equal to 0 at DC what we have is R infinity, this becomes infinity, C0 becomes, the impedance becomes infinity, and all other parallel branches simply reduce to resistances. So, what we have is a series connection of R infinity and summation Ri in series with a capacitor of value C0, and therefore Z of 0 tends to 1 by C0 s, s tends to 0. At origin it is this capacitor which takes over, and obviously Z of s shall have a pole at the origin, alright, and this is why the subscript C0 here. But we shall derive this in more details. I just wanted to make an observation because it is obvious here that at DC all we have, the equivalent impedance is that of a capacitor of value C0. At infinite frequency the equivalent impedance is that of a resistance of value R infinity. Okay. Now, if I write an expression, pardon me, at s equal to 0 what we have is, you see, each of these parallel branches, this is open and therefore Ri takes over. So, at s equal to 0 the equivalent circuit would be R infinity C0 and then this is what it is, R1, R2 and let us say Rn. So, at DC this is a series RC combination, and compared to infinity the resistances can be ignored. So, the function z of s blows up at s equal to 0 and z of s limit s tend to 0 tends to 1 by s C0. In other words, it has a pole at the origin of residue 1 by C0. Is that correct? Residue is 1 by C0, not C0. Okay. But if you look at this network once again, the most general RC network, R infinity C0, and then you have a number of Ri's and Ci's in parallel. If you write an expression, an analytical expression for this, you see that z of s is equal to R infinity plus 1 by C0 s plus summation over I. What is the impedance of this? If this is Ci, Ri divided by S Ci Ri plus 1, okay, as simple as that. Ri parallel 1 by Sci is this, which I can write as R infinity plus 1 by C0 s plus summation I. I want to write this in the form of a polynomial in which the leading coefficient is 1, that is, I want to make the pole obvious. So, I want to write this as s plus 1 by Ci Ri, then the numerator obviously shall be 1 by Ci. Is that okay? So, the most general form, from this observation we say the most general form of an RC impedance, Z subscript RC of S would be K infinity. Now, let us do away with the with the elements and write in the general form of residues and poles. I shall have K infinity plus K0 by S plus summation over I Ki divided by S plus sigma I, where sigma I is a real positive quantity and is equal to 1 by Ci Ri. One of the properties of an RC impedance is obvious now, that its poles must be on the negative real axis. There can be a pole at the origin and there can be poles at S equal to minus sigma I, where sigma I has to be positive. And therefore, one of the properties that is obvious from this form, K infinity, I am talking of RC only, K infinity plus K0 by S plus summation Ki divided by S plus sigma I over I. One of the properties is that poles on the negative real axis. Is this point understood? Only poles cannot be anywhere else. Since this is the most general form, the poles are obvious. What are the frequencies at which the function blows up? Obviously, it can blow up at s equal to 0. Now, origin is also a part of the real axis. Okay, it is as good a part of the imaginary axis as of the real axis. So, poles on the negative real axis only. This negative real axis now includes s equal to 0. Okay, and what can you say about K infinity, K0 and Ki? They are truly the residues. Unlike LC functions in which you wrote Kis divided by s squared plus omega I squared, those Ki's were twice the residues. Here these are truly residues. Okay, K infinity, is K infinity a residue? No, there is no pole at infinity. There cannot be a pole at infinity. Don't you see that at infinity the value is simply K infinity. At infinity this becomes 0, all of them become 0. It does not have a pole at infinity. So, K infinity is not a residue. You see the difference between LC and RC networks. LC networks must have either a pole or 0 at infinity. Here this is not the case. At infinity the RC impedance is a constant. Now it's another matter that this constant can be 0. K infinity can be 0. If it is 0, then the function has a 0 at infinity. But under no circumstances can a ZRC of S have a pole at infinity. If this is the general expression, it simply cannot blow up at infinity, and therefore for ZRC pole at infinity is barred. It cannot have a pole at infinity. Alright, K infinity is not a residue. Is K0 a residue? Yes, it is. K0 is a residue. It is a residue of the pole at the origin if this pole is there. If it is not there, then at the origin what is the situation? If there is no pole at the origin, if K0 equal to 0, then what is the situation at the origin? It is a, is it a pole? Is it a 0? No, it is a constant. Don't you see, if this term is not there and you put S equal to 0, then you simply get K infinity plus summation Ki over sigma I, correct? So at the origin an RC impedance can have either a pole or a constant value, agree? At infinity an RC impedance, alright, let me repeat, at origin an RC impedance can have either a pole or either a pole if K0 is not equal to 0 or a constant value. What is the constant value? K infinity plus summation Ki over sigma I. At infinity the ZRC of S can have either a constant value which is equal to K infinity or a 0 if K infinity is equal to 0. Okay? And you see the difference between LC and RC. Okay? K0 is a residue, Ki is also a residue. So what can we say about the residues, about the nature of residues? How did we identify what is K0? K0 was 1 by C0, and therefore K0 must be real and positive. Similarly Ki it was 1 by Ci, and therefore that must also be real and positive. So all residues must be real and positive. Must be real and positive. It cannot be any other way. Any questions so far? Now, I could do this for an RC admittance also. If I take, I am taking a slight detour to bring another point. That is, what I am trying to do is, I have concluded that poles are on the negative real axis. What about the zeros? Can the zeros be anywhere else? To show, to come to a conclusion about this question, about the zeros of ZRC, we look at the poles of YRC. Okay? Now, what would be the most general form for an YRC? Obviously, we take the Foster 2 form of LC and replace each L by a resistance. So what we get is this, some R, and for reasons to be made clear, we call this R0. Then we have a capacitance, we call this a C infinity, and then we shall have a parallel connection of several branches, each consisting of a series connection of a resistance and a capacitance Ci. This is the most general form for an YRC. Agreed? Now, therefore, I can write YRC of S as equal to 1 over R0 plus C infinity S plus summation admittance of this series combination. What is the admittance? 1 over Ri plus 1 over S Ci, which I can write as 1 over R0 plus C infinity S plus, oh, I beg your pardon, I made a mistake. 1 over Ri plus Sci. No, 1 over Ri. How can I make so many mistakes at one go? Am I right now? Okay, thank God. So I can write this as Sci divided by Sci Ri plus 1. Agreed? Agreed? Okay, let's do this. Let's do a further bit of simplification. I must have your undivided attention, total attention, because things can become confusing. RC impedances do not have the same properties as RC admittances. Unlike LC, you see ZLC and YLC, they have the same partial fraction expansion. It is not the case here. You see the difference. I can write this as S plus 1 over Ci Ri, and I can write this as 1 over Ri multiplied by S. Agree? I have written the denominator in terms of a polynomial, the leading power of which is unity. And you notice that the most general form for an RC admittance would be, oh by the way, do you understand why I have used the symbol R0? You see at DC everything is open, capacitor is open, these are open, and therefore it is only this resistance R0. So R0, 1 by R0 is the value of YRC at S equal to 0. And you can also appreciate why I have used C infinity, because at infinite frequency this is a short, impedance short, correct? So the admittance blows up. Admittance has a pole at infinity with a residue of C infinity. All others, this resistance, all other resistances, they are large compared to a short circuit, and therefore at infinity YRC of infinity is dominated by C infinity, and this is why this subscript C infinity. Okay. This is just an observation, on the wayside observation. Now the most general form therefore shall be of the form K0 plus K infinity S. If you want, we can use a different symbol, because we used K for the residues, but I think it should be clear in the context, okay, plus summation I Ki S divided by S plus sigma I. This is the situation. If you, let us use a prime, if you compare this with ZRC of S, ZRC of S is of the form K0 by S plus K infinity plus summation I Ki divided by S plus sigma I. If you compare these two forms, obviously you see that these are not the same forms, okay, these are not the same forms. Not only that, these Ki primes, okay, K infinity prime, is this a residue? Yes, it is. Is K0 prime a residue? No, because at DC you look at YRCS, it cannot have a pole at the origin. At DC S equal to 0, you put this vanishes, and you are simply left with K0 prime. So at DC YRC can only have a constant value, or if this constant value is 0, that is if the initial R0 is not there, then YRC can have a 0 at the origin. Alright. So the behavior at the origin for YRC and ZRC are different. ZRC can have a pole, YRC cannot have a pole. On the other hand, at infinity ZRC cannot have a pole, impedance cannot have a pole, at infinity no way, but YRC can have a pole, alright, because of K infinity prime S. K infinity prime is truly the residue of YRC at S equal to infinity. If it does not have a pole, if K infinity prime is 0, then what is the value at infinity? Constant. It is K0 prime plus summation Ki prime, no sigma I. because at s equal to infinity it is the highest power term k I prime s and s. So, at infinity the value would be simply y r c infinity shall be k 0 prime plus k summation k I prime, alright. But the most important deviation is that this k I prime is not a residue. Do you understand this? It is not a residue. If you write a partial fraction expansion, obviously partial fraction expansion should have been of this form, that is a constant divided by the pole factor. It is not in that form, it is multiplied by s. But can you identify k I prime as residues of some quantity? Obviously, if you divide y r c by s, then k I prime would be residues. So, you make the observation here, k I prime are not residues of y r c of s, but they are residues of y r c of s divided by s, if you divide by s. Agreed? The major conclusion that we wish to derive from this expression is about the poles of y r c. Where are they located? Obviously on the negative real axis. Could there be one at the origin? No. There cannot be a pole at the origin of y r c, but its zeros are still on the negative real axis. I am sorry, the poles. The poles of y r c are the zeros of z r c, isn't that right? Because z and y are reciprocals of each other. Poles of y r c must be the zeros of z r c, and the conclusion therefore is that poles and zeros of R C driving point functions, either impedance or admittance, it does not matter, must lie on the negative real axis. Okay. So, let us make this statement. Poles. Okay. So, there are specific locations on the negative real axis which are barred for poles. There are specific locations which are barred for zeros, but no pole or zero can be outside the negative real axis. They cannot be on the imaginary axis. They cannot be complex. So, the statement is poles and zeros of R C dpi's are on the negative real axis. This is one of the properties of R C dpi, f of s, f R C s, which is either z or y. Poles and zeros of R C driving point impedances are on. No, this is not a strong statement. Let us make it stronger. Only are only on the lie, not are, lie only on the negative real axis, nowhere else. Let us make it strong statement. Poles and zeros of R C driving point impedances lie only on the negative real axis. Second, I get by looking at the expressions for y r c, which is k 0 prime plus k infinity prime s plus summation k I prime s divided by s plus sigma I prime, and at z r c, that is k 0 by s plus k infinity plus summation k I divided by s plus sigma I, no s. Okay. I have written this again and again. Now, if I look at this, you notice that if I divide y r c by s, what are the terms that I get? I get k 0 prime by s plus k infinity prime plus summation k I prime by s plus sigma I prime, which is exactly the same form as z r c. Isn't that right? And therefore, I can make this statement that y r c by s and z r c are form equivalent. They are exactly of the same form, and this I write as triple equality sign, triple line, triple horizontal line with an f. F stands for form. Y r c by s and z r c are exactly equivalent in form. and this is a statement which has million others inside it. What it means is that the residues, this is equivalent to stating that residues of ZRC and YRC by S are real and positive, okay, because they are form equivalent, and we also showed independently that k sub I primes, k infinity prime, k 0 prime, they should all be real and positive because they relate to a component value. Okay. Now ki primes are residues of YRC by S. Question: suppose I find the residues of YRC, not YRC by S. Suppose I find the residues of YRC. Would they be real? Would they be positive? It turns out that they are real but strictly negative. Okay. This we shall show by demonstration. We will not prove it. That is, residues of YRC, simply YRC, if you do not divide by S, are real and negative. Now, because they are negative, they are useless for us. We can't utilize them, all right. Because they are negative, we cannot use that partial fraction expansion. So, it also follows that if you wish to synthesize a given YRC in Foster 1 form, then you have to first divide by S and then expand in partial fraction. You understand what I mean? If you have a function, if you have a realizable, a positive real RC admittance function, and you want to realize in Foster 2 form, then you must first divide by S, carry out the continued fraction expansion. You divide by S, carry out the partial fraction expansion to find out k 0 prime, k infinity prime, k I prime. Then you multiply by S. All right. This is Foster 2 synthesis of an RC DPI. Foster 1 is simply expand ZRC. Foster 2 is expand YRC by S. You see the difference between the two cases. All right. The next property that we derive, which is also useful, you remember that in the case of LC, the poles and zeros alternate. Poles and zeros alternate, okay. And the first critical frequency is the origin. Origin is either a pole or a zero. The last critical frequency is infinity, which is either a pole or a zero. You will see that both of them differ in the case of RC. To derive that, let us look at ZRC of sigma. Since poles and zeros of RC impedances as well as admittances lie only on the negative real axis, it makes sense to talk of RC impedance or admittance on the negative real axis. You see, in the previous case, in the LC case, our poles and zeros were in the j omega axis. So, what we did was we took a ZLC of j omega and put that equal to j x of omega. Capital X we called what? Reactant, not susceptance, reactance. And similarly, YLC we put S equal to j omega. Why S equal to j omega? Because the critical frequencies are on the j omega axis. And then we put that equal to j times B omega, where B is susceptance. Now, in this case, naturally it makes sense to talk of the impedance functions or admittance functions on the real axis. So, let us take ZRC sigma, that is k 0 prime plus I beg your pardon, k 0 by sigma plus k infinity plus summation k I divided by sigma plus sigma I. Now, if you differentiate this, yes, I am taking an impedance function. If you differentiate this with respect to sigma, in the previous case, in the LC case, we showed that dx d omega or dB d omega are strictly positive.
So it's k infinity and k 0 by sigma.
Yeah, that is what I wrote. Impedance function, so it can have a pole at the origin. The value at infinity is infinity, k infinity, and then ki divided by sigma plus sigma I. What is the objection about this? I have simply put s equal to sigma, nothing else. Now, if I differentiate, notice that it would be minus k0 by sigma squared, k infinity differentiated would give 0, and what about this term? It would be minus summation ki divided by sigma plus sigma I whole squared. And you see that each of these quantities are positive, and therefore this slope of ZRC on the real axis would be strictly negative. Strictly negative. It was strictly positive in the earlier case. And if you take YRC, put S equal to sigma, and take the differential coefficient with respect to sigma, you can similarly show, what is your guess? This would be strictly positive. You see, impedances and admittances behave differently. Why can it not be 0? Good question. If it has to be 0, since this cannot be 0, this cannot be infinity, that k0 and ki's, all of them have to be 0. Pardon me? All of them have to be 0. Then we are talking of a pure resistance. Alright? Pure resistance is a degenerate case of an RC impedance. That is not something we are worried about. We are worried about an RC when the capacitance comes into the picture. That is why we said this is strictly. Okay? What we said is right. We actually should put less than equal to 0, but equal to 0 is a trivial case, and therefore we take that out of consideration. Similarly, if you differentiate YRC, it is very easy to show that it is strictly positive. Okay? Now, if that is so, let us take ZRC to be specific. D ZRC sigma, D sigma is strictly negative. Okay? And the behavior at S equal to 0, is either a pole or a constant. Pole or a constant. What is the constant value? Pardon me? It is k infinity plus summation ki divided by sigma I. Okay? This is the constant value. At S equal to infinity, it is either a constant equal to k infinity or what is the other possibility? 0. 0 occurs if k infinity is equal to 0, and therefore there are 4 possible combinations for an RC impedance. You see, there are two possibilities here, 2 here. If you make a combination, I can have constant at the origin, constant at infinity, constant at origin, 0 at infinity, pole at the origin, constant at infinity, pole at the origin, 0 at infinity. Right? There are 4 such cases. Okay? Of these, one case is interesting, that is constant at origin and constant at infinity. Which constant is greater? No. If it is constant, then obviously, see, this is, oh, I am sorry, you are right. The DC value is greater than the value at infinity. Agree? Not only that, if you go back to the expression for ZRC, it is k0 by S plus k infinity plus summation ki divided by S plus sigma I. This was the expression. If I take ZRC of j omega and the real part of that, can you tell me what this is? This is k infinity. This will be purely imaginary. This is k infinity plus summation. What shall you get here? Ki. sigma I divided by sigma I squared plus omega squared. Agreed? What is the minimum value of this? What is the minimum value of this expression? Obviously k infinity, which occurs at omega equal to infinity. Isn't that right? As omega increases, this term monotonically decreases to 0 at infinity, and therefore the minimum value of the real part of z of j omega is equal to k infinity. K infinity therefore has a very special significance. Not only it is the value at infinity, it is the minimum value of the real part.
So
and yes,
previously we took S is equal to sigma.
S equal to sigma, that was to find the slope. If you want to find the real part on the j omega axis, this is what you have to do. And we showed in positive real function testing that this is an important quantity. This has to be non-negative. And we also showed that from any positive real function, if the real part on the j omega axis varies like this, then the global minimum value we can remove. Agree? Without the function becoming non-positive real. Okay. I brought in this only to tell you that this constant infinity can be removed easily, can be removed without destroying the positive real character of the function. But you cannot remove z0. You cannot remove this, because if you do that, then you are making, then at some frequencies the real part would be negative. Okay. So, let us look at this. Let us take a specific case. Let us say the function is constant at s equal to 0. Take a ZRC which is constant at s equal to 0 and constant at s equal to infinity. This value is ZRC of 0 and this value is ZRC of infinity. Then let us plot ZRC of sigma versus sigma. Okay. We have taken this case, constant at s equal to 0 and constant at s equal to infinity. If the constant at s equal to 0 is this value, let us say z of 0, then the constant at s equal to infinity must be lower than this. Isn't that right? Must be lower than this. Suppose this is the value. Suppose this is z infinity. Both of them must be real and positive. Must be real and positive. Okay? Because z of s is a positive real function. Okay. Now, the slope dzrc d sigma is strictly negative. So, starting from here, as we go towards the negative real axis, how can it go? Can it go down? No, it has to go up. There is no choice for it. It has to go up. If it goes up, where should it go? It has to go up monotonically. How far can it go? It can go up to infinity, which means that the first critical frequency must be a pole. Is that clear? No. You see, the function, I am plotting ZRC sigma on the negative real axis. All right. The function has to go up because the slope is negative. It has to go up. It cannot come down. If it could come down, then we could have the possibility of a 0. All right. The function has to be strictly, the slope has to be strictly positive. Okay. Strictly negative. What strictly negative means that it cannot have a maximum or minimum. Isn't that right? And therefore it has to go monotonically. How far can it go? It can go to infinity. All right. Let it go to infinity. If it goes to infinity, obviously there must be a pole there. You know that at a pole the function changes sign, and therefore after the pole it must rise from here. It must rise. It cannot fall. From minus infinity it must rise. So the next critical frequency must be a 0. And then it should continue to rise. So it rises, which means that the next critical frequency must be a pole. Yes, it can take negative value. If sigma is negative, obviously it can take negative value. You see, positive real function simply says if S is real, Z of S is real. It does not play. Okay, what can happen next? Next, it can repeat. It will rise from here, then it can go through a 0, it can go to another pole. But suppose that is the end. Suppose there is no further poles, then obviously there will be 0 here, and the function will asymptotically go towards g of infinity. The message that we get from here is that first is poles and zeros must alternate. We cannot have two adjacent poles or two adjacent zeros. Why not? Because then the slope will not be strictly negative. If there are two adjacent zeros, for example, okay, then it must go up and then it must come down. So the slope has to go through 0 and then positive, which is not permitted. Similarly, we cannot have two adjacent poles. Why not? Because then what is happening? Slope has to be positive. Okay, so it must come down and then it must go like this. It must come up and then go without crossing a 0. So this is not permitted either. Number 1, poles and zeros must alternate. Number 2, observation, the first critical frequency has to be a pole. One might argue that this is not the only situation. The function could have a pole at the origin. The behavior at origin is only one of two possibilities. One of the possibility is that it might have a pole at the origin, or it is a constant at the origin. If it is a constant at the origin, then we see the first critical frequency is a pole. If it is a pole at the origin, obviously the first critical frequency is a pole. So in either case it is a pole. The last critical frequency is a 0, irrespective of whether the function attains a constant value at infinity, or what is the other possibility? 0. If it attains a 0 value at infinity, obviously the last critical frequency is a 0. If it attains a constant value, then also the last critical frequency must be a 0. So our conclusion from this diagram is, first, poles and zeros alternate. Poles and zeros are only on the negative real axis, so you can add this on the negative real axis. And number 2, for ZRC, first critical frequency is a pole, last critical frequency is a 0. Can we, without further derivation, can we say what will be the first critical frequency of an YRC? That is right. First critical frequency of an YRC is a 0, and last critical frequency of YRC is a pole. These are the differences, and one should not get lost in these differences. You must, after a while, you will remember. If you remember the first critical frequency of ZRC is a pole, then you can remember everything else. If the first is a pole, last has to be a 0, and for YRC it is exactly the reverse. Okay? So one of the statements, you remember just one of the statements, and I find it very convenient to remember this, that the first critical frequency is a pole. Alright. Now these peculiarities of description of ZRC and YRC, that puts a lot of restrictions on the synthesis. Let us take some examples. Let us say S plus 1, S plus 4, S plus 8 divided by S times S plus 2, S plus 6. The function is given. It is not said whether it is an impedance or an admittance. It is not said whether it is RC or not. First thing is you find out whether it is RC. if it is RC, poles and zeros must be on the negative real axis. Poles and zeros at 0, minus 2, minus 6, minus 1, minus 4, minus 8. Okay. So, poles and zeros satisfy that condition. Do they interlace? 0, minus 1, minus 2, minus 4, minus 6, minus 8. Yes, they do interlace. Then, is it an impedance? It has to be an impedance because the first critical frequency is a pole. If the first is a pole, last must be a 0. Last is minus 8, it is a 0. So, this is indeed a ZRC. Let us take the next one, S plus 1, S plus 8, S plus 2, S plus 4. Can it be an RC immitance function? No, why not? Poles and zeros do not alternate, and therefore this is not an FRC. Okay. The next one, S plus 2, S plus 4, S plus 5, S plus 8. Yes? No. 2, minus 2, minus 4, minus 5, minus 8. Okay. It cannot be. All right. Agreed? Okay. Next. S times S plus 2, S plus 1, S plus 3. What about this? This has to be YRC of S. Okay. 3 times S plus 2, S plus 4, S times S plus 3. Yes? ZRC? Okay. Let us look at, this is a ZRC. Let us look at a synthesis of this. If I want to synthesize this, then I write this in terms of its poles. Does it have a pole at infinity? It cannot have a pole at infinity if it is ZRC. So, at infinity, with a little practice, you will be able to write down the value directly. What is the value at infinity? No, 3 times 2 times 4 divided by 3, 8. Okay. It is 3. 3s square divided by s square. All right. Plus, what is the value at 0? What is the residue at 0? Origin is a pole. 8. So, it is 8 by s plus only one pole, only one internal pole on the negative real axis, s plus 3, and the numerator shall be some constant k. What is k? K you find like this, multiply this by s plus 3 and put s equal to minus 3. It is 1? All right. Agreed, it is 1? All right, it is 1. Therefore, the circuit is simply 3 ohm resistance, a capacitor of value 1/8, agreed. Then a parallel combination of a resistance and a capacitance. The capacitance is 1 and the resistance is 3 or 1 by 3. Come on, this is an impedance, so 1 by, it must be an admittance. How much? 1 by 3. And the synthesis is complete. We could do this by Foster 2 also. If we do it by Foster 2, then we take YRC. YRC is S into S plus 3, 3S plus 2, S plus 4, and there comes a problem. We do not expand YRC, we expand YRC by S. Therefore, this is S plus 3 divided by 3, S plus 2, S plus 4, and I expand this as K1 divided by S plus 2 plus K2 divided by S plus 4. I would urge you that you try expanding this in partial fraction. You will see that you get negative residues. It is only this way that you can do, and finally you find out YRC and synthesize this. We will continue this in the next lecture.